So this is temperature time diagram of tempering. So tempering definition I told, it consists of heating of the hardened samples to the predetermined temperature, soaked there for sufficient time, and then cooled slowly below lower critical temperature as per the requirement. So tempering's objectives are, first objective of tempering I told, to relieve the internal stresses. Second objective I told, to increase the toughness. And third objective, to eliminate or transform the retained austenite. Okay, as per the desired stages in the tempering. So this diagram you have seen. This diagram is temperature versus time diagram. Long form I will tell what is it. Okay. So this is lower critical temperature. There are 3 stages in the tempering. So your next title you write down stages in the tempering. Let this figure be above it, no problem. Explanation of this figure I am giving now. Stages in the tempering. It may be also called as types of tempering. In bracket, types of tempering. Now, for confusion, many students get confused. In last class, we have studied types of hardening. Which are these types of hardening? Conventional hardening, quenching in stages, os tempering, and mar tempering. So even the word tempering is there in os tempering and mar tempering. These are the types of hardening. Remember, don't get confused with the word os tempering and mar tempering. Os tempering and mar tempering are the types of hardening. Okay. Now types of tempering I am telling. First, low temperature tempering. LTT I have written. Low temperature tempering. Second, medium temperature tempering. And third, high temperature tempering. Low temperature tempering, medium temperature tempering, and high temperature tempering. Now pay attention. Attendance record I will mark. 1 minute, just attendance record I will mark. Okay. So low temperature tempering means what? Now hardened samples are heated in the range of 150 degrees Celsius to 250 degrees Celsius. That is the range of low temperature tempering. What happened? Your hardened sample, what is the microstructure? Microstructure of hardened samples. May I erase this figure? I will erase. Microstructure of hardened sample is having martensite plus retained austenite. Martensite plus retained austenite. Okay. Now, when you are going to heat this sample once again, what will happen? At 150 to 250 degrees Celsius, that is the range of martensite only. So your retained austenite is converted into low carbon martensite. Retained austenite is converted into martensite because of this reheating, and little loss of hardness of earlier martensite is there. Overall, this will give martensite only. So, because of reheating of hardened samples at around 150 degrees Celsius, the retained austenite is converted into low carbon martensite, and little compromise in hardness of earlier martensite is there. Overall, hardness is little reduced, no far reduction in the hardness, but toughness is improved. This example I have given few minutes before. If original hardness is 50 RC, because of reheating, it may become 43 to 45, but additional property of toughness is achieved. Low temperature tempering treatment is given to usually high carbon steels and alloy steels, where we don't want to reduce much hardness. In that case, we have to maintain the hardness. That's why only elimination of retained austenite is okay, and then low carbon martensite produced from it, that is also okay, and we will achieve our desired properties. This will happen by heating at 120 to 150 to 250 degrees Celsius. Now, this is LTT. What happened in medium temperature tempering? Your martensite plus retained austenite, it is converted into martensite plus alpha plus Fe 2.4C. This is benign. Retained austenite is converted into benign because heating here is 150 to 250 degrees Celsius, and here is 250 to 350 degrees Celsius. This is benign zone. So austenite is FCC. Recall whatever I told earlier. Whenever there is a phase transfer is only possible from FCC. Retained austenite is FCC. When you heat, soak and cool, that FCC, even you are not crossing 727, you have some FCC. That FCC is converted into this alpha plus Fe 2.4C. It is called as epsilon carbide, and this structure is called as bainite. Now, see the heating temperature. Whatever earlier hardness of martensite is there, that is reduced to little lower level. For example, here before tempering, if hardness is 50 RC, and if you carry out low temperature tempering, your final hardness after low temperature tempering will be 45 RC, 5 to 6 digit loss, but toughness improved. But heating temperature is more. In second case, always remember, if you heat harden the sample, martensite will lose its carbon and hardness affects. So here in original 50 RC becomes 38 or 40 RC only. Little more loss of hardness. Okay. But here, whatever written austenite is converted, that is into bainite. So some compromises takes place and your improvement in toughness with sufficient hardness is there. For example, you have 50 RC. If you suppose some specimen which is coming under shocks, for example, spring. Generally, medium temperature tempering is given to the springs, links, and similar components where it is subjected to shock. More hardness 50 RC, but less toughness, it is not desirable. So little compromise in the hardness and improvement in the toughness, overall increase in the properties will increase the life of component. Hence, medium temperature tempering will give sufficient hardness. I'm not using more now. It gives sufficient hardness and good toughness so that life of the component increases. So here 5 degree loss digits, here 10 to 15 digit loss, no problem. Now third, see. So here I will give example, I am going to dictate, don't worry. High carbon steels, alloy steels, tool steels, where you want to maintain the hardness. Here some more requirement is of impact resistance. So this is carried out usually spring and similar applications. And third is high temperature tempering heat. Martensite plus written austenite is converted into low carbon martensite plus perlite because heating temperature is 450 to 600 degrees Celsius. Perlitic zone. So whatever hardness of earlier martensite, 85 or 90%, that will always complete loss. Very small hardness remain. And whatever written austenite is there, that written austenite is converted into perlite, alpha plus Fe3C. Now, very interesting. Original hardness is 50. So low temperature tempering will give hardness 45 RC. Medium temperature tempering will give hardness 38 RC. And high temperature tempering will give hardness 15 RC. 1.5. This is usually similar to the hardness of perlite. So if you carry out normalizing treatment, whatever fine perlite you have, its hardness is around 15 to 20 RC. Now, if just normalizing is heating, soaking, and cooling in air. If simple treatment gives this hardness, why to go for hardening and tempering and achieving this hardness? Very interesting. This is the interview question. Write it somewhere. Even normalizing gives around 15 to 20 RC just by heating, soaking, and cooling in air. Low cost process. No any cooling media is required. you can keep in atmosphere. But hardening require cooling area, means quenching baths are required, maintaining the temperature of quenching bath, that is a costlier process. Secondly, you are following it by tempering, again tempering furnaces are required. So hardening, tempering will be very costly process, and obtaining 15 RC to 20 RC. So that will be costlier manufacture or this treatment process. This sample, suppose both are of same material, I have carried out normalizing for this. Cost of process is 100 rupees. Okay. Similar component, I have carried out hardening, tempering. Cost of process is 500 rupees. If I check hardness of both, this hardening tempering will give 16 RC and this normalizing will give 15 RC. One digit here and there. Why to waste this 500 rupees? Friends, if you compare the working properties many times, see, always cost is not considered. There are many requirements. If you improve, if you check the strength of both components, I said 2-3 digit more for hardening and tempering than normalizing. That 2-3 digit more are also playing important role. I repeat, only normalize the sample give hardness 15 RC and hardened and tempered sample, hard tempered tempering, that gives 16 to 17 RC, 2 to 3 digits more. For 2 to 3 digit, why to waste almost 5 times the working cost? The answer is, in many of the applications, these hardened and tempered samples maintain their strength than normalized samples. So both objective is same, but process is different, and rarely this treatment is followed with special requirement because it is costlier. So when you want little more hardness, you have to follow hardening, tempering, and that is a high temperature tempering. Okay. So question may be asked, which is similar process to normalizing? So normalizing gives fine perlite. Similarly, hardening, tempering, that is high temperature tempering, will also give perlite and low carbon martensite. So little martensite is present here. That's why comparatively this process gives better hardness. Okay. This is used for connecting rods, gears, crankshafts, camshafts. Crankshafts, connecting rods, if you are normalized, and the same component if you hardening and high temperature tempering, life of second process is more. It is observed with experiment. That's why people are following it. Okay. Now write down. First, low temperature tempering. It consists of heating of hardened samples, to 150 to 250 degrees Celsius. 150 to 250 degrees Celsius. Soaked there for sufficient time. And then cooling in the air. Full stop. Retained austenite. Now make star mark to this statement. Retained austenite is converted into low carbon martensite. Retained austenite is converted into low carbon martensite. Full stop. With little compromise, with little compromise in the hardness, with little compromise in the hardness, comma, toughness is achieved. Toughness is achieved. Full stop. This is used for high carbon steels and alloy steels. Second, medium temperature tempering. Underline dash. It consists of heating of the samples to 250 to 350 degrees Celsius. You can say 250 to 400 also. 250 to 400, alright. 250 to 400 degrees Celsius. Soaked there for sufficient time and cooling slowly in the air. Next line, star mark. Retained austenite is converted into alpha plus Fe 2.4C. Alpha plus Fe 2.4C. That is benide. It gives sufficient hardness with improved toughness. Full stop. It is used for applications like springs. Third, high temperature tempering. It consists of heating of the samples, hardened samples to higher temperature in bracket less than A1. Bracket complete. That is 450 to 600 degrees Celsius. 450 to 600 degrees Celsius, comma, soaking there for sufficient time and cooling slowly in the air. Full stop. Next line. Martensite loses the carbon. And retained austenite is converted into perlite. retained austenite is converted into perlite. Full stop. Much loss of hardness. Much loss of hardness and higher improvement in the toughness. Higher improvement in the toughness. Full stop. It is used for crankshafts, camshafts, connecting rods, gears, and similar components. Now next line, make star mark. Even the hardness of hardened and high temperature tempered. Even the hardness of hardened and high temperature tempered samples is near to only normalized sample, only normalized or just normalized sample, only normalized sample, comma, former treatment gives better mechanical properties. Former treatment gives FORMER. Former treatment gives better mechanical properties than latter. What is meaning of this statement? Former, this is a style of writing English sentence. Former treatment is hardening and high temperature tempering, and latter treatment is normalizing. So instead of repeating the same words, I have given former treatment gives better mechanical properties than latter. Means hardened and high temperature tempered sample and normalized sample even have a similar hardness, but better mechanical properties are there for former treatment. And last sentence, hardened and or former treatment is costlier than latter. Former treatment is costlier than latter treatment. This is all about tempering. So just in short, I will explain. Tempering is always followed after hardening. For which reason? For relieving the stresses, for improving the toughness, and for transforming retained austenite. I repeat once again, tempering is always followed after hardening for relieving the internal stresses, which is produced by quenching. Second, for improving the toughness, and third, for eliminating or austenite. Okay. Now, many times what happened? There are certain alloying elements which may disturb this response. So these certain alloying elements are usually phosphorus, sulfur, and other elements like manganese. So when you heat these samples instead of in the tempering, so there is decrease in the toughness and improvement in the brittleness. This is not true for all processes, but for certain types of steels. This is because of presence of these particular alloying elements, and that concept is called as temper embrittlement. Write down title. Temper embrittlement. EMBRITTLEMENT. Temper embrittlement. I repeat spelling. TEMPEREMBRITTLEMENT. Underline dash. This is one of the disadvantage. This is one of the disadvantage during tempering of particular steels. It's not all particular steels. Full stop. When these steels are tempered, in the range 350 to 650 degrees Celsius, 350 to 650 degrees Celsius, and cooled slowly, comma, instead of increase in the toughness, comma, brittleness increases. So brittleness and toughness are two opposite properties. Brittle means it will have poor shock absorption capacity. It will break into pieces immediately. Okay. Next line. This property is called as temper embrittlement. This property is called as temper embrittlement. Full stop. This occurs usually for the alloy steels. This occurs usually for the alloy steels having elements phosphorus P, phosphorus, tin, Sn, antimony, Sb, nickel. So if your steel have these elements, you may see during tempering reverse effect observed. Why? There are certain different reasons. So these elements are resisting for the improvement of toughness. Okay. Now how to eliminate? Next line. Temper brittlement can be reduced. Temper brittlement can be reduced by addition of elements like molybdenum, titanium, zirconium, and by increasing the rate of cooling. Okay, this short note was asked 2 to 3 times earlier. That's why I have dictated. So tempering aim is to improve the toughness. This you remember. So all treatments are covered. Now one important property. So yet we have not completed this chapter because main part B of chapter is case hardening. There are 4 to 5 types and their subtypes are there that I am going to take in next class. But one important concept before we go to next type or next part of the hardening. So that important concept is hardenability. It is a very important concept. Without understanding hardenability concept, you may not survive in the core companies as a metallurgist. So that concept I will explain in detail in next class. Okay. So please convey message to your friends about attendance. So unfortunately, they are not understanding in spite of calling from CC, etc. Okay. So here we will stop for today. Thank you.